You got a system of parametric equations. X equals f of t, y equals g of t. And you're trying to find the distance traveled. Remember what parametric curves model? They model motion. In general, the motion could be along some crazy curve that goes all over the place. You know, pretend you're looking straight down in a parking lot and you're in a car turning back and forth like this. Doesn't have to pass the vertical line test, but you're after your distance traveled. It's the same as the arc length of the curve. You could say S is the arc length, but you could also say it's distance traveled. And without fully explaining why, the distance traveled, even when you're going around some weird curve, whether it's in the plane or in three-dimensional space, it's still the integral of the speed. This is still the integral of the speed over the interval. But what is the speed? Speed can never be negative. It's not like velocity. Velocity for back and forth motion could be positive or negative, whether you're going left or right or up and down. Velocity for curvy motion in the plane or in space, a bug flying around, is a vector. Velocity for curvy motion is a vector, an arrow that at every moment in time points in the direction of motion. Like at this moment in time, it would point like that, and have a length equal to the speed. That's called the velocity vector. And as you move around the curve, it changes. But no matter where you are, it's always tangent to the curve. What is the length of that vector? If you get into vectors enough, you'll see that the velocity vector has what are called components that are the derivatives of these functions, f prime of t and g prime of t. And its length from the Pythagorean theorem turns out to be the square root of f prime of t squared plus g prime of t squared. Now, you can also relate this to the other arc length formula. I don't want to take the time to do that. Suffice it to say, this integral can be hard to do as well. If we consider the example of a Lissajous curve, take, for example, f of t to be cosine of 3t, and g of t to be sine of, say, 5t, some other frequency, the parametric curve that you can make with parametric plot with this kind of syntax, say t goes from 0 to 2 pi, curves all over the place. There it is, Lissajous curve. And if we try to do the integral, what is f prime of t? Well, what does square root of f prime of t times squared plus g prime of t squared look like? We're trying to integrate that function there. You can't use cos squared plus sine squared equals 1, for one thing, because 25 and 9 are different, but for another thing, because the frequencies, angular frequencies, the 5 and the 3 are different. If you try to get Mathematica to integrate this, it says, I give up. It doesn't know what to do. It doesn't even have some other name for it, like ERF or Fresnel. I mean, you could make up your own name for it, and maybe you could be famous for that. I've never tried. You can patent formulas, but you have to pay money to do so, and nobody may care. But you can numerically integrate it. The integral does exist. The area under the speed curve, which I can plot. Here's the speed graph. Goes up and down. It looks like it's 0, but the origin's not in the picture here. Looks like it's 0 sometimes, but it never reaches 0. It goes up and down. It's speeding up and slowing down all the time. It's still got an area under the curve. It's a continuous function. But you have to numerically integrate it and integrate the speed. You can't do it symbolically. about 24.6. That's the distance traveled, the arc length of the curve. Okay. So in practical problems, you often have to use numerical integration.